So very good morning to all of you. Myself Anil Sharma from Impulse Technology. So this today's training session basically will cover up the presentation about the software, and then we'll also show you the live training on how you can model different kind of solar cells applications. Due to some technical problem, I could not be able to issue the licenses, but the training will be done on whole day so that you will have complete capability that software can do it. So let's start the presentation session for 15-20 minutes. Then we'll deliver the live demo on the softwares. So first of all, I would like to introduce about our company, parent company, that is called Fluxim. So Fluxim is basically a Switzerland-based company that is based in Switzerland, which provide or which developed the software as well as hardwares. The equipment for R&D, for solar cells, LEDs, different kind of solar cells, LEDs, and they provide their product, software, including hardware to industry and academia built by. The company was founded in 2006 by Dr. B. Trussler as a spin-off from Zurich, and they have developed a couple of simulation tools. I hope my slide is visible to all of you. So I want to introduce about this Fluxim, that is our parent company, which is based in Switzerland and which developed the software as well as hardwares, the simulation tool for theoretical predictions, as well as the equipment hardware for characterizations of optical and electrical semiconducting devices. So the software and hardware they developed and provide industries and academia worldwide. The company was spin-off from Zurich University of Applied Science and founded in 2006 by Dr. B. Trussler. If we talk about the product, there is one of the product called SETFOS. The SETFOS is basically a semiconducting thin film optics simulation software, which works on transfer matrix, diffusion, absorption calculations for cells and LED simulations for small area devices, one-dimensional applications. When you work on large area devices, the device of the your structure increases in micrometer, millimeter, then the LAO software is also developed for large area semiconducting devices, where you can also minimize the optical electrical losses and PV module applications. So these are two different products, SETFOS and LAOS. SETFOS is for cell simulation for small area devices, and LAOS is for large area, and to minimize the losses, then this LAOS is required. Even other hardware is also there for characterizations. So if you see, there is an equipment that is called PIUS, this third one. PIUS is basically for electrical optical characterization, where you can measure different around 15 measurement analysis, including IV characteristics, impedance characteristics, and many DCAC and transient analysis. With this flows is there for ELPL measurement, electroluminance, photoluminance, angle dependent, ELPL at a time angle dependent measurement flows is there on different angle, 0 to 360 degree, 0 degree to 360 degree angle dependent ELPL measurement. For degradation of LED, this lithosis is there. For stability analysis, hysteresis, MPP tracking, maximum up to 56 channel, the degradation, hysteresis analysis, lithos light is there. So not only a simulation tool company are developing, they have developed the software as well as hardware for simulation, and experimental can be validated. That's why the company are working on experimentally and theoretical, both at a time. This is about different portfolio of the company which are available. Now, if we talk about the SETFOS software, because today's training schedule on SETFOS. So SETFOS is stand for Semiconducting Thin Film Optics Simulation Software, which is works on organic application, perovskite application, tandem application, silicon application, amorphous silicon, tandem perovskite, solar cells as well as LEDs, quantum LED, perovskite LED, for novel optoelectronics thin film based device simulation, for optical calculation, electrical calculation, and optoelectrical calculations at a time. So in this particular different things can be done. We can optimize our layers, we can optimize the parameters, and we can try to improve the efficiency of our devices virtually based on theoretical prediction by using the SETFOS softwares. The main domain of the software are for organic solar cells, inorganic solar cells, perovskite solar cell, tandem solar cell, perovskite tandem, silicon tandem, heterojunctions, thin film, dye-sensitized, organic photodetectors, quantum dot, organic LED, perovskite LED, quantum LED, white LED, and thermally activated delay fluorescence with high fluorescence LED applications, multiple emitter layers. So this is specifically for optoelectronics domain. For LED solar cell, it could be a different type of solar cells and LED. How it can be done very quickly and easily, what type of advantages are there, I will discuss in the coming slide as well as in the coming time with a live demonstration by sharing and making the live solar cell in my screen. Now the company has created multiple modules. So software are divided in 4 modules. One is called Absorption module, Diffusion module, Advanced Optics module, and Emission module. Software are divided in 4 modules. So according to your requirements, according to your particular needs, whatever the module is convenient for you, you can plan accordingly. This absorption module is required for optical property calculations. Whenever you want to analyze how much the light will get absorbed by your particular material, for that kind of optical calculations, this absorption module is required, where light absorption, photocurrent calculations, ISC value calculation, for that analysis, absorption module. For electrical property calculations, diffusion module is there, where you can measure, you can calculate the IV characteristics, Venn diagram, semiconducting, active layer can be defined by using diffusion module. It includes the electronic charge, excitons, ion charge, anions and cations, traps, multiple traps, SRH recombination, Auger recombination, Langevin recombination, biomolecular recombinations, multiple type of traps are included that can capture your electron holes, DC simulations, AC simulations, transient solvers, IMPS, IMBS, intensity modulated photocurrent, photovoltage, spectroscopy, Hoping interface models are there for tandem devices, polar layer, and optoelectrical calculation. You require absorption module and diffusion module. Both the modules are required for optoelectrical calculations. For optical analysis, only absorption. For electrical analysis, only diffusion. For optoelectrical calculation, absorption as well as diffusions. So these are 2 common modules which required for solar cells applications. If you go beyond that, you want to work on texturing, surface texturing, nanoparticle, quantum dot, birefringence, Fourier, root mean square setting, ray tracing analysis, then texturing some raw data you want to import. In that case, this advanced optics module is required, where the layer structure is not flat. You want to see the effect of nanoparticle on that. In that case, this advanced optics module will be required. And emission module is required for LED application. Many people work on both the application. Many people work on only solar cells application. That's why the software are divided in multiple modules. Whatever the module is required according to your particular need, you can plan for that. So this emission module for emitting devices, where you can see the outcoupling layer, emission spectrum, ELPL analysis. For this, emission module is required. This is all about brief idea about the module. Now I want to show you the advantage, few advantage on the screen. Many advantage, unlimited opportunity are there in the tool. So if we talk about the software advantage, it is a completely a user interface based tool. You have no need to learn the Python or C, C++, Java, no language necessary to learn. Everything will be plug and play. You have to concentrate on physics. You have to concentrate on the parameter, on whatever the models that can enhance the efficiency of your devices. So that's why the complete user interface is there, very quickly, easier to learn, where plug and play options are there. You can select the desired parameter and the software will quickly build your structures. You have to find out that which parameter and how much value should we give as an input. It can generate your all results in standard presentation format. Your data can be exported in standard common format in terms of text format or Excel format. In image format, the data can be exported. It supports the ion transport model, anion and cation with hysteresis effect. Windows, Linux, even Mac OS is also supported. In current version, Mac OS, Windows, Linux, there is no barrier on the operating system. Any type of operating system supported with the default convergence parameter, default parallel calculations, surface texturing, interface parameter, AFM or BHDF roughness data you can import on your air layer or active layer in between. So the texture data can be imported. DC simulation, AC simulation, transients, impedance analysis, unlimited number of layers. In some software, there is limited number of layers is possible. Only 6 layer or 7 layer. But let's suppose you are making two cell together, silicon perovskite, silicon tandem devices. When layer number of active layer beyond 10, then other software may be fail to simulate that structure. But software SETFOS can simulate unlimited number of semiconducting layer in the devices. So either you want to simulate LED or you want to simulate the solar cells, unlimited number of layers, active layers can be defined and you can simulate it. You can find the optical property of the particular material, absorption, total device absorption when the device layer stack is completed. So optical layer wise, optical analysis, device wise, and optical analysis. Many new features are coming day by day because there is a dedicated team who is developing the different features, whatever the new research are going in solar industry. So software are updating regularly. We can provide you the technical support on how the software can be used effectively, including the nanoparticle effect, metallic effect on your devices, multiple parameters you can optimize. Let's suppose you don't know the thickness of your active layer, as well as voltage biasing, current biasing, wavelength, temperature, multiple parameter you want to sweep, you want to optimize. So there is a provision where you can define the minimum value, maximum value, and the interval for calculations. How much interval in between the minimum and maximum, and software will do the calculation by single click, and it will give you the predictions that what could be the optimized value for this particular thickness or particular voltage or particular wavelength or temperature. So that kind of multiple parameter sweeping and optimization is available with the tool. Even the LED module is also inbuilt for emitting devices, for CIE, color diagrams, radiance, ELPL measurement. The emitting option is also there. Multiple state-of-art mobility models are there. So as you know, the efficiency of the device is depend on the models. What kind of trap parameters, what kind of recombinations, what kind of excitons, temperatures, state-of-art mobility model, doping models. So these are couple of models are implemented. How it can be used, that I will demonstrate you in the live demo on the software. But state of art mobility model are there, recombinations are there, traps are there, excitons are there, anion and cations are there, and many more features are there, including DC, AC, transient simulations are available. This is all about cell simulations. SETFOS is one-dimensional, solar cells and LED application. When you go beyond that, if you're already using such kind of software and you want to work on module simulation, you want to increase the area of the devices, you want to work on PB module application, then we have another package, another software. These are two independent software. There is not a inbuilt module in that. These are two independent software. This software works on large area organic semiconductor devices, where you can work on 2D plus 1D, two-dimensional plus one-dimensional FEM-based software. One-dimensional in the sense, escapes 1D or SETFOS, whatever the other software data is there, you can import in this LAO software. And you can find the losses. To minimize the losses, electrical losses, ohmic losses, heating losses, sun losses, to optimize electrode geometry. In that case, this LAO software will be required. This software also contains the 3 modules for electrical module, electrical analysis, electrical losses analysis, electrical module, heating losses, thermal module, optical losses, optical module. So these are also divided, whatever the module required. According to that, you can choose the minimum modules also. So this works on large area, PB module, active matrix, AMOLED device applications. Now, if I summarize that, I have introduced you about SETFOS, LAOs, and some equipment from the Fluxim company for electrical optical characterization, degradation, stability of the perovskite application, ELPL measurement by using philos. So these are optoelectronics, solar cells, LED, software as well as equipment for characterizations. When you go for atomistics level, quantum level, then we also have some nano academic technology product where atomic or molecular level, nano decal, rescue, including quantum TCAD, spin qubit, semiconductor, quantum device simulation software is also available from other vendors, other companies. So these are multiple software. All are from one from Switzerland and this is from Canada. So other product information we can discuss later on because today's session is dedicatedly on SETFOS software. And if we talk about the indigenous project, many people work on experimental. For the experimental purpose, we provide the probe stations. This is a stainless steel made probe station from semiconductor analysis and testing solutions. Semiconductor analysis testing solution, that is one company. We are the manufacturer of these equipment. These are basically a stainless steel made probe stations, where it is a single stage probe, the 2 probe, 4 probe, or even micro probe, octagonal probe can be created. It is customized. We can customize according to your requirement that probe station. It is a vacuum compatible chamber where you can place your sample and we can create the environment under different temperature, vacuum, pressure, and cooling, heating, light source we can also provide you. So from -30 to 200 degrees centigrade sample you want to characterize without needing of liquid nitrogen with the gas condition, humidity condition, we can also characterize the sample. So that characterization of sample is also possible. We also provide the sample holder where you can put your sample on this 6-pixel sample holder. You can also selector is also there, which you can select the sample and you can place this sample holder inside your solar simulator and it can measure your IV characteristics and other parameters. This is our indigenous product that we are manufacturing in India. We can discuss about it. If I talk about the usual list of SETFOS in India, The SETFOS are widely used in India. It is using by IIT Madras, BHU, NIT Karnataka, Bhopal, NIT Srinagar, IIT Guwahati, IIT Allahabad, Chandigarh, Arunachal Pradesh, Kerala, Berhampur University, SRM, Jawaharlal Nehru Center for Advanced Scientific Research, Bengaluru, MDU Rohtak, IIT Roorkee, and many more are already in pipeline where they are going to give us the orders very soon on Impulse Technology. So these are some customers which are using SETFOS in India. So I have given the small presentation about different product as well as the SETFOS, and this is my contact information. If you want to know more details about different product that which you are interested, you can drop the email or you can call, you can email or WhatsApp on this contact informations. You can take the screenshot or photo of this my detail, and you can contact me after this training. Then I can help you whatever the product you are interested, or I can try to convince you or technically satisfy you and find and give you the solutions to achieve your goals in this research domain. Whatever the research you are doing it, I can try to provide you all the solutions. So thank you for listening constantly about the presentation session. Now I will go to the demonstration where I will open the software and try to model one solar cell in the beginning first, then LED, then Tandem Perovskite, and different other structure. We will try to model today in front of you and do the calculations and visualization of your output. So thank you for your patience. Now I will go for the next live demonstration on SETFOS, where the SETFOS is already installed in my computer. In my laptop, it is already installed. So I will try to demonstrate from my system by sharing the screen. So I would like to open the SETFOS 5.5. So 5.5 is the latest version which recently launched. So semiconducting stands for semiconducting thin film optics simulation software. But I want to open as an administrator so that we can provide full privileges. I can give all permission, backend permission. Now this is new feature window. Whatever the new features comes, because the company are developing many new features in every 3 months or 6 month time, and they pop up on top of the screen. So I want to close this new feature window. Would like to show you the main screen. Now this is our main user interface of SETFOS. Now we will try to create one project from scratch. So first of all, if you see, there is an option called help. The manual is provided, tutorial is also provided. Once you click on the manual, it will open one PDF file where so this manual and tutorial will basically have background information of physics, models, equations, and how you will start working on the software. That information is given in the tutorial. If someone required this information, I can also share you the manual and tutorial so that the background physics and how to start working on the software, you can get to know from the manual tutorial. So first of all, I want to create one new project, then manual and tutorial will be open. Now I want to start from scratch. So I'm clicking on the new option to create a new project. Once I click on the new button, the new empty project has been created. It is a simple empty default project. Now we will customize it. We will optimize it. We will create from scratch. Now, as I told you, I'm trying to model the solar cell structure first, then we'll model the LED and other devices. For solar cell application, first of all, we require the optical module for optical analysis. So this certain button is there. As in the presentation, I introduce you about 4 modules: absorption, depth diffusion, advanced optics, and emissions. So I want to enable the absorption module by clicking on this absorption button. I have enabled it. Once I click on it, this absorption setting is enabled. For optical calculation, this absorption module is good enough. Only optical analysis can be done. But I want to perform the electricals also. So I will enable the depth diffusion module as well. I click on this depth diffusion battery sign. Then this depth diffusion module, which you can see this tab, it is also enabled. Whatever the module you are interested in, that you may be purchased, that module functionality will be enabled, something will be disabled, dependent on your package which you may be interested. Now these 2 modules has been enabled, which I introduced you about the PPT, and this absorption depth diffusion setting has been enabled. Now this is the first structure, is layered structure, absorption, depth diffusions. In the layer structure tab, we have to create our layer stack. Our device stack will be created in this particular regions. Let me try to create the structure. There are 3 by default layer are there: surrounding, unnamed, and substrate. I am assuming all viewer are as a beginner, so I'm creating from scratch, and I'm trying to explain you from beginning as a layman to all of you. Now I will click on this plus sign, which indicate to add the layer. So to add the new layer, I have clicked in between the substrate and surrounding. The unnamed layer is selected, and the layer will be added in between the surrounding and the substrate. Below the unnamed, the number of times I will click, the number of times new layer will be added. So how many layers are there in your device stack? That number of times you can click on this plus button, and that number of layer will be added. I can add many number of layers. If I will click more number of time, there is no limitation of number of layers. You can take 10 layer, 15 layer, 20 layer. $30 layer, any number of layers you can add or delete. This is for addition of new layer. If you want to delete any layer, there is a minus sign is there. You can click on this minus sign to delete the layer. And there is other options called change the position of layer to down, to change the up position. Means you can change the layer, one layer to up location, down location, or you can inverse the location. Duplicate layer can be created if multiple multiple active layer you want to use, then duplication is also possible. Position can be reversed, or multiple options are there in this vertical tab. Now let's suppose this is my number of layers that I want to create the stack. Now from top, my light will come from the top. In this case, the light will come from top. Let's suppose I want to define here from the substrate side. I want to take from the layer. So this is, let's suppose my top electrode is called FTO. FTO as a metallic electrode. The next layer I want to take as an example TiO2. Next layer I want to take as an example perovskite. Next layer I want to take spiro. And then I want to take the next layer, it's called aluminum. So one ETL, HTL, perovskite, and surrounding. Now this is my layer stack. Initially, I have defined only the layer name. I have to define the properties also. Now these layers, whatever I had added, I have to define the thickness also. So let's suppose my FTO is having 100 nanometer. We have other option, micrometer, millimeter, wavelength dependence. So whatever the unit you want to take, you can take accordingly. Then I can define that my TiO2 layer thickness. As an example, let's suppose I want to take 50 nanometer. My this perovskite layer, I want to take 300 nanometer. And this spiro, 50 nanometer. And this my aluminum, 100 nanometer. And this surrounding, there is no meaning of surrounding thickness. So I mentioned 0 as an example. Now this is my layer stack. And this layer stack you can also visualize on the right side. Initially, I have defined only the name as well as thickness. Property is not assigned yet. I will assign the property now because I am creating from beginning. So I will do everything from scratch. How to create the new materials also. As well as I will show you the material library. Now, if I see here, these all materials, we have to assign the optical material, refractive index data, that is N and K value of each layers, as well as some active layer in between the electrode, semiconducting properties as well. First of all, we have to assign the refractive index. So let me try to create one material files. Initially, I am not going to import from my existing library. First of all, I want to show you how to create the new material and how the new material can be uploaded on our software. So I take the notepad first. This is my notepad. In the notepad, to assign the refractive index, as an example, I am creating the refractive index data. So let's suppose FTO refractive index file I am creating. I have other provision as well. I have an option where I can import from library of software as well. But initially, I don't want to import from my library. I want to create the material my own. So this is one refractive index which I'm creating. My first column is wavelengths in nanometer. My second column, which I'm giving the real part, and third column is imaginary part. So I can give the hash command also so that I can understand this is the wavelengths. First column is wavelength, second column is N value, Third column is K value. This is real part, imaginary part of refractive index. If the refractive index is not constant, it is dependent on wavelengths. So by following this procedure, I can define the next value of my refractive index, N value, wavelength value, and K value. So I can follow this procedure to create the new materials. I am not importing initially from library. I am trying to write the material optical data. Either this data I can experimentally find out, or I can get from open source library. That is called one of the library I know, that is SOFRA index, where you can find some optical refractive index data, or you may find some literature. In some reference paper, some optical refractive index may be given. So I am assuming this value. Whatever your value is there, you can put it. I'm assuming this much of value. I can define multiple options. So till now, like on the bottom side, I can continue, or I can define n number of times below that. Whatever the range of wavelength is there, let's suppose the fourth value I'm taking 450. This is the random value which I'm taking for FTO refractive index. You can find out from some source also. Now, I can take 500, 600 wavelength, 700 wavelength, 800, 900, whatever the range of that particular material which you are going to use for your solar cells or LED. Click on File option and click on Save As. Now on desktop, I want to save the name of my refractive index. So as an example, FTO refractive index, and I will change this save as type and select all, and mention here the extension, because the software will take NK extension for optical data. That's why I mention FTO refractive index .nk and selected all files. So that .nk extension of refractive index material will be created, and then click on save. Now this refractive index material file I created from scratch, which I will use here. So what I will do, if the value of refractive index is constant, it is not dependent on wavelength, then simply you can mention here 1.5. If wavelength dependency is not there, if it is dependent on wavelength, the same procedure which I explained in the notepad, where you can put the wavelength, real part, imaginary part, next value of wavelength, real part, imaginary part, then continue, go on that and mention that number of value. Now here I will import that file which I created, that NK. That's why I given this .nk extensions. So I will select here file separated .nk file. I select file tabulated. It was in the form of tabulated. Instead of separate value of NK, we have taken tabulated. So I selected tabulated NK file .nk. I click on this import button. Now I will browse that folder. Browse that folder because I saved on my desktop name of FTO minus refractive index. So this file is present here on the desktop. You can find here FTO minus refractive index.nk, which I can upload. Now this upload, I can view here the wavelength, real part, imaginary part. Wavelength in the x-axis, y-axis, real imaginary part is mentioned. So this is a new material which I created. This is a new material which I created and imported. Now same procedure, if you see the material which I created here, which I created, the value of the refractive index data for this FTO material. I created in the notepad and save as .nk. Save as .nk by selecting file type as a all. And this material file has been added on my desktop .nk. Now, this is one procedure. Similarly, if you want to create the refractive index data of other material, let's suppose this is a TiO2. I click on it, the new material, new layer has selected. And here, similarly, I can mention the other refractive index value. Let's suppose this is 490. And I can mention the other value as example. I'm assuming this value, but as per your particular need, you can change or you can create the new refractive index data and click on this file option and click on save as. And let's suppose this is my TiO2. Few of the things I have changed, modify it, and click on file, save as, and this is as an example. I'm assuming this value, but whatever your value is there, you have to put it your value, not mine value. And I will select here, save as all files, tabulated refractive index TiO2.nk, and click on save. And it will save on my desktop. You can see this is a TiO2 refractive index.nk. It's created. So by following the same procedure, you can create new material refractive index data, and then you have to upload that tabulated in the table format data NK file. Click on import, choose the location where the file is present, TiO2.nk refractive index, and click on open. It will upload like that. So this is FTO, this is TiO2. Now this is the new material which I created, saved, and then uploaded. But the data which I imported may not be much accurate because I had taken the random value. Now I want to import the refractive index exact value from my library. So there is an option called import. If you want to modify more, let's suppose you want to edit the material file which you created, then there is also provision where you can edit the option in this editor. So whatever the value we mentioned here, we can also mention in this optical material editor. So you can mention that value in this script as well, or this graphical form also. This is graphical representation where you can mention the value here, or wavelengths and K. 3 values are there. If you will modify here, you can save as new file, and then again new material can be added. So another provision is given to modify the existing files. And then if you modified it, you can export it. If you will export it, you can future the new file, whatever the modification you have done, that material file you can upload it. So you have to create it, upload it. If you want to modify the existing file with the new material, you can modify and export. And then future again, you can import. This way, it will save a lot of your time in again and again creating the file. Now, I want to show you the library of the material which given in the database, in the software database. So if you will click on this import optical material file, there is a one library of material of NK file given in the SETFOS database. This is SETFOS database where many type of file are present. .nk extension represent the refractive index data. Other extension I will also discuss later on, but maximum file you can present here .nk extensions. N means real part, K means imaginary part of refractive index data. So this is the way where I'm scrolling right, and you can find a lot of material are given in our library. This is lot of material which are given in our library. So whatever material you want to use, either from the library or how you can create from scratch, that I demonstrated. By following this procedure, by type mentioning in notepad and save that file, then you can also import. So let's suppose FTO, I select the F from the keyboard and find the fto.nk file. So this is fto.nk file. I will choose it and open it. Now, if you see here, the fto.nk file has been uploaded. Similarly, I will click on this TiO2 layer. I will import from the library for this TiO2 layer. So I type here T and find out TiO2.nk file. Select it and click on and uploaded this real part, imaginary part. If you want to see the value, click on edit button and check on the script side. This is a script side, you can check it. Now I will click on Perovskite, upload the tabulated file from the library. So, dear participants, sorry, very sorry. There are some network issue or electricity failure in the company. So, I'm really sorry for that. I want to resume my services. So, I hope my screen is visible.
Yes.
Can you please confirm my screen is visible?
Yes, sure.
With this. Okay, perfect.
Yes, visible.
Yes,
So
yes,
let me
confirmed.
continue the session. So sorry for that. There was some failure in the internet network. So I want to continue. Now here I have defined all layer refractive index data. Now for optical absorption profile. Like this is absorption. This is substrate, FTO, TiO2, perovskite, spiro. So which layer is getting more absorptions? So that absorption is P polarized, S polarized. Accordingly, this absorption rate it is. Energy flux, illumination, spectral, absorption profile, in which region it will eliminate, white absorption profile, white absorption, spectral absorption profile, and other layer specific total device absorption as well as absorptance. Absorptance for FTO layer. This is FTO layer. This TiO2 layer will be the green layer, and this perovskite layer will be the pink layer absorptance, and this layer will be this behind that. One overlapping it is, you can find this layer it is here. So each layer absorptance you can also find. So for optical analysis, photocurrent and other analysis, this absorption module is required. Let me perform the electrical calculations. So I will enable the depth diffusion settings. Once I will enable the depth diffusion setting, we have to mention that which layer as an electrode type, which layer as a semiconducting type. So FTO, I want to use as an electrode. Aluminum, I want to use as a back electrodes. And in between the FTO and aluminum, this is called the active layers. So I can mention TiO2 semiconducting, perovskite semiconducting, spiro as a semiconducting. FTO as electrode, aluminum as a back electrode, spiro, perovskite, TiO2. So ETL, HTL, and perovskites, these are three semiconducting layers. As an example, let's suppose I want to simulate. I have defined all optical property of each layer. Now, in between electrode, active layer is there. So we have to define the active layer property also. That is semiconducting property. So for this FTO, we have to mention the type of electrode. Either it is a ohmic type or it is a thermionic type with their work functions. Let's suppose this is a ohmic type FTO and work function as an example 4.4. And similarly for aluminum, It is mentioned 4.5. I want to take 4.8. Now, work function of electrode are defined. Now, this TiO2 perovskite spiro is there. I want to define the semiconducting property. Once you enable this drift diffusion mode, so in the semiconducting tab, either you can create a new material file by following the same procedure. In Notepad, the syntax is different. Syntax for semiconducting property is different, but it should also be written in the Notepad. If you see here, in semiconducting, there is a multiple tab: charge, excitons, traps, mobile ions, recombinations. So we have to enable particular options in that. So if I click on this charge option, you can see the charge Lumo is there. For the time being, I want to hide this layer structure tab so that I can visualize my complete back end of this charge transport property. To enable it future, I can again click on it. I can enable it. If you see here, this is called energy levels, Lumo value. So initially, TiO2 layer is selected. You can see back shadow is there, back shadow is there. So energy level, I have to mention the TiO2. I'm taking some mid-level value of for TiO2 HUMO level 7.46 and LUMO is equal to 4.2. This is HUMO energy level for this TiO2. Then I want to take effective density of state, that is called N naught, and which I want to take, let's suppose 1.8 e to the power 18 per centimeter cube. Similarly, I can take, let's suppose 2.2 e to the power 18 per centimeter cube. So this is effective density of states. Then next option is called dielectric constant. As an example, I want to take dielectric constant of TiO2 as example 9. Then I go beyond that. I go down by scrolling the scroll down. I can find the acceptor doping, donor doping. So I can enable the doping type, and here I have to take either acceptor type or donor type, P type or N type. Let's suppose I want to make the donor doping and constant donor doping. Wavelength dependent, other dependent option is also there. But initially I want to take 1 e to the power 19 per centimeter cube as a donor doping of the TiO2 layer. And optical generation efficiency should always be 1. Now the next layer is called mobility model. There is a constant mobility option is there, field dependent, field temperature dependent, extended Gaussian type disordered, correlated type extended disordered, field dependent mobility file. This is multiple options for state of art mobility. Initially, I want to define constant, but if you want to take temperature, then the parameter will be enabled according to your selected mobility model. Whatever the model you will select, the parameter will be enabled, and you have to give the input of electron holes parameter of the mobility models. I want to take constant type. Let's suppose electron mobility mu E is equal to I want to take 20 for the TiO2 layer, 20 centimeter square per volt second, and for hole, let's suppose I want to take 10 centimeter square per volt second. So all the semiconducting property of this particular layer is defined. For this TiO2 layer, whatever I defined, HUMO, effective density of state, dielectric constant, donor type doping, and electron and hole mobility. So charge transport parameter are finished. Now next tab is called excitons. So excitons is mostly people are work on LEDs, but some people are also trying to get on solar cells as well. But I have not worked enabled any exciton parameter in solar cell. But if you want to add it, you can click on add button. The radiative decay rates, non-decay rates will be enabled. We will discuss in the second half about excitons tabs. The next tab is called traps, electron traps. So once you click on this trap, you can click on this enable trapping for this material. Click on enable trapping and click on this add button. Once you click on add button, you have to define the traps parameter, acceptor like electron trap, donor like hole trap, and trap density parameter, trap energy parameter, and other related parameters. So let's suppose in this TiO2 acceptor like trap is there, where the trap density is equal to, I want to take 1 e to the power 15 per centimeter cube. Similarly, the trap energy 1.63 electron volt below the LUMO value for this TiO2. And if I will go to this capture rate, electron capture rate, hole capture rate, I have to enable and select the default value or the constant value or temperature dependent. So I make a constant value, electron and hole capture. I want to take 1 e to the power minus 10 centimeter cube per second, and 1 e to the power minus 10 for hole and electron. Both I want to take same. Now this is a traps parameters, trap energy, density, electron and hole capture rates. Then I will go to the next tab that is called mobile ions. If you want to define the anion and cations related mobility model, then you have to enable the anion and cations and associate the density parameter and mobility parameter with that. Up to infinite maximum density you can take for anion and cations. Initially for this particular example, let's suppose I don't want to include any ion parameter. I go to the recombination. Sorry, I enable only one trap. I also enable the donor like trap as well. So I enable the only single acceptor trap. Now in this second tab, when I click on add button, I also need to enable the donor hole traps, and where I have to mention the value of trap density for hole as well. So I want to define 1 e to the power 15 per meter cube per centimeter cube. Trap energy 1.63 for hole electron volt above HUMO value. This is for hole electron and hole capture rate constant. I can take constant and define its value 1 e to the power minus 10 and 1 e to the power minus 10 per centimeter cube per second. So electron hole capture, trap energy, trap density, and both the things are enabled. One is for acceptor like trap, electron trap, second one is for hole trap in this TiO2 layer. Then I will go through this trap coupling, which is enabled here. I go to the mobile ions. I don't want to enable the ion traps, but this trap, I have to enable the trap recombination and this bulk recombination. Here, the Langevin recombination model is enabled. In the bulk Langevin recombination,
There is no sound. Yes. Now you are audible.
Now I want to run the simulation and I want to enable one sweep setting. So this is toggle sweep setting where I can apply some voltage or any parameter, whatever I want to sweep. So let's suppose voltage, I want to sweep from minus 3 volt to plus 3 volt with an increment of 0.2. So 0.2 interval from minus 3 to plus 3 volt, it will run the calculations. So simulation is running and you can see the simulation is calculated. Simulation is done and this is a IV plot. Now let me see here from minus 1 to plus 0.5, we can check the analysis. So I will change the value of voltage biasing from minus 1.5 to 0.5 with increment of 0.1 interval. So let me run the simulation by changing the input parameter. You can see the curve of the IV graph will be like that. Power conversion efficiency, power density. We want to see the display key figure. You can see the efficiency that I have achieved around 12%. We will multiply it here. This is the maximum power conversion efficiency. This is the maximum power density. Maximum power density in milliampere per centimeter square. Fill factor, JSC, BOC. These value I have got it. If you want to change other more parameter, you can click on it. You can click on this run button. Now you can see this is the IV curve. IV curve. So whatever the fine tuning you want to do, you can do that tuning. So I'm taking the random value. So you can manipulate your structure and accordingly the simulation will be done and you can visualize your output like that. You can zoom that particular region. And similarly, the other analysis, if you want to see the Venn diagram, this is for Venn diagram from negative biasing to positive biasing. So from negative to positive biasing with HUMO-LUMO, energy reference, Fermi level, charge density plot, electrical field in the graph, as well as in this 2D representation, mobility plot, recombinations, trap captures, and many more things are there. Even photocurrent value, absorptance, layer specific absorptance. So this is all about the brief summary. This is all about the layer absorptance analysis, particular material, either it is a TiO2 layer, this is for perovskite layer absorptance, this is for spiro layer absorptance, and stack contributions. So here you have seen, I have sweep only voltage. If you want to sweep multiple parameters, let's suppose you want to sweep the thickness also. So you can click on this plus button where you want to sweep the thickness of, as an example, perovskite layer. So I mentioned perovskite, D is equal to thickness. And if you want to see the thickness, 300 I mentioned. But let's suppose you want to see 200 to 500. with increment of 20 nanometer steps. So 200, 220, or I can take 10 nanometer also, and I can run it. So 2 parameter at a time, it will run the simulations. We can take it 3 parameter, 4 parameter, 5 parameter, 6 parameter. Maybe the density could be affecting the output, mobility could be affecting thickness, refractive index, voltage, wavelength, temperature, whatever input you are giving, you can sweep and optimize the value. That's why the multiple parameter option will be there here. You can see I can click on this plus sign again and again, and multiple tab will be enabled. This is the calculation log window, which is showing the percentage of simulation completed. And once the result generated, will display here the result generated. So now since it is going to finish the calculation, since I have defined the iteration point is equal to 10. If I will mention the number of steps is equal to 20, then simulation time will be more less as compared to the existing one. So everything depend on the iterations. The simulation time depend on iteration, but 2 minutes, 4 minutes, 5 minutes, 10 minutes. It is a very fast algorithm. So it is about to finish the calculation, and then I will show you the output. This tab will be enabled once the finished calculation 100% achieved. This result tab. Now it is done. You can see, click on device current, and if the thickness is changing, you can see this is active perovskite thickness from 200 to 500 nanometer. Then how the device current is reflecting or varying the output. Similarly, the power conversion efficiency on different thickness value of active perovskite layer. So the multiple graphs are plotting accordingly. You can take that number of steps. If you want to see only one value, you can take all value, or it can show a single value also. So the variation in your output, how it can affect, including the current maximum power, fill factor, if this visualization, it will also show that. All the key figures. And if you want to take another parameter, let's suppose you want to take another layer thickness variation, refractive index variation, temperature variations, spectrum variation, current density, or you want to take work function of FTO, you want to vary as an example, then work function can also be vary. Whatever the input you are taking it, multiple parameter at a time, you can sweep and optimize that value. Now here I have taken the spectrum AM 1.5. But there is other provision where the location and time dependent. You all people are located on different locations. Some of them may be in Bombay, some of them are Chennai, some of them are Kolkata, Delhi, Hyderabad, Bengaluru. So different location may have different spectrum. So that's why there is a provision of latitude, longitude, elevation, date, time, cloud, weather. azimut, angle, because the cell may affect based on the location as well. So the realistic spectrum, there is some algorithm, there is some model, smart implemented model is there. That model information given in the manual and tutorials. I can share you the manual tutorial later on because some PDF viewer is there. I can show you that manual tutorial where you can find the information about the theory, about the algorithm. So if I show here, I can show you the manual tutorial. This is the manual and tutorial. So it will open in your PDF. There is some PDF viewer not responding in my system, but I can open you. Try to open in the Microsoft page. So this is can open the Microsoft page. You can see here, and in this everything from scratch. How we can model any kind of solar cell that given in the tutorial package. And if you see the manual, in the manual you will get to know the background physics, background models, equations which implemented. So all information related to models, physics, background, algorithm, background information about the charge transport model, recombination model, Auger recombination, simplified SRH recombination, traps, distributions, excitons. So these information are given in the manual so that you will have not only the front end, you should get to know about the back end physics implemented in the software in the algorithm. So these all information, parameters, sweeping, everything are given here. So the help can be taken from the manual and tutorials. Even if you want to know the publication paper and more information, this is a main website, fluxim.com, where you can go to the research publication. Actually, there is some internet slow in my PC. So I'm changing my network. So you can scroll this website, fluxim.com, and where you can find some videos, scientific blogs, publication list, and all product information which I presented in my PPT. So these are we are supplying in India optical characterization, solar cell and PV module applications. And we also manufacturing some probe station for sample characterizations. So I want to introduce one of our partner from Gandhinagar, PWPU. So my partner is there, Dr. Darshan here, who joined our meeting. He will represent about probe station, how the experimental setup can also help you to achieve the simulation results with the experimental. So Darshan sir, thank you for joining the session. I request you, you can share your screen, conductor analysis and testing of samples for characterization of experimental.
Namaste, Sharma sir. My
Darshan sir,
audio is
can you hear
visible.
me?
Hello, my screen is visible to you?
Okay.
Am I audible, sir?
Yeah, you are audible. You are audible.
Yes. Thank you, Sarma sir, for wonderful introduction. Myself, Darshan Kumar from the Semiconductor Analysis and Testing Solutions. Here I am welcome you to all. Just a little brief about the product and services regarding this. We are a manufacturer of the semiconducting testing equipments like the micro probe station, optoelectrical characterization systems, automatic reaction kitters, hydrothermal autoclave, and industrial chillers. Also, we are the excels in the providing the automation solution for the scientific research and industrial applications. Additionally, we are the offering the AI/ML courses for the material science researchers and the cutting edge innovation and efficient solution for the industrial application also. We are committed to advanced research and solutions to make the preferred partner in the semiconductor industry. Also, we are delivering expert quality performance across our products and services. These are our services. We are the manufacturing in the semiconductor testing equipments. Also, we are making the precise, reliable, and efficient cutting edge research
Your
solutions. Yes.
slide is not changing. It looks your slide is not changing, and it is not full screen.
It's hand.
Okay, just a second. Now it is okay, sir.
Yeah, it's okay now. You can make full screen.
Now it is not in full screen mode.
No.
Okay, just a second.
Yeah, it is full now. It is full screen now.
Okay, as I told previously, we are offering the AML courses for the industry as well the researchers. Also, we are the providing the process control or an efficiency, enhance the outcome of the research and make the automated solutions for the research laboratories as well the industries. Also, we are making the custom solution. Also, we are offering the solution for the industry and researcher, providing to scientific instruments and automation for the advanced research and applications. Also, we have our recently launched our web designing and development products for the research laboratory as well the companies also. These are our products. From the first 4 images, you can see that there will be the 4 type of different application based micro probe stations for the application of solar cell, thin film, FETs, gas sensing, as well as the semiconductor material, as well the optoelectrical characterization. I will brief discuss in afterwards. So the next product is the pixel switchable thin film solar cell sample order. Also, we discuss in further. This is the one sun light source. Light source is based on LED based one sun light source. Also, we are manufacturing the industrial water chiller. Also, we are manufacturing the PEC setup for the hydrogen generation. We are manufacturing a hydrothermal autoclaves as well as the automatic reaction kitters. Or another product is the battery tester. Let's start with the micro probe stations. We know that the micro probe station is the widely applicable in the field of semiconductor and the material science, because we know that the probing is the keynote tool for the characterization the semiconducting samples. So what we are offering in this product is that this is the compact in size. The chamber size is almost 23 centimeters. So it is the tabletop micro probe station. Also, there we are having the 4 micro probes, which are made from the pure tungsten, and the tip size is the 50 micrometer is the fine tip size. And the stage is having the facility of heating and cooling. So there will be the no liquid nitrogen requirement. And also the stage can provide the temperature of minus 40 Celsius to 120 Celsius without liquid nitrogen. And another, we are providing the stage is having the room temperature capability of the room temperature to 350 Celsius temperature range. So as per your requirement, we are manufacturing the stages. Also, there will be in the lead of this chamber, there will be the quartz optical window. From that, you can luminance your sample. And also we are providing the one sun light. And it is also having the facility to control the intensity through the feedback process. So you can vary the intensity.
Slide is not changing. Did you change any slide?
No. Right now I am discuss regarding the micro probe station.
Okay.
So you can change the light intensity from 0.2 sun to 1.2 sun based on the optical setup. Also, this setup
I have
is
one query.
Yes, please.
During the intensity testing, are you going for the CRI, chromatic index, and CCT? Are you testing all these?
Sorry, your voice is little breaking. Please ask again.
I'm questioning again.
Yes,
When
yes.
you are going for the illumination testing of the light intensity, are you going for the test or CRI, CCT of light?
Yes, definitely. We are providing this certificate.
Acha, are you providing? That means LED
Yes.
and OLED lights, or even if you go for the solar illumination lighting, bifacial, all this, are you giving the certificate?
Yes.
Okay, thank you.
Yes. So we are providing the also wavelength calibration also will be there. So you can we are providing the wavelength, color, temperature is all our light parameters. We are giving as a certificate that means this light is matching these parameters. Also, the chamber is having the high vacuum capability. It is 5 into 10 raised to minus 2 torr vacuum capability. So in this system, you can characterize a different type of characterization, something like gas sensing. There will be the port for the rotary pump. Also, if you don't require that much amount of the vacuum, you can connect the diaphragm pump through the chamber. So at a time also there will be the provision for the MFC. You can connect the MFC through this chamber and control the flow rate and make the gas characterization setup. Also you can use this sample. Also there will be the optical window in the lid of this chamber. So from the top side you can emit the light for the optoelectrical characterization. And as per your requirements, we are changed the stage size. We are offering the 4x4 centimeter stage size recently. And in the first image, you can see that there will be the 4 micro probes that will be controlled in XYZ direction. So you can precisely put your samples and get the contact. In the another micro probe station, there will be the 2 stages. First stage is for the thin film. We know that when films are connected to some probings, they make some scratch on the sample. Also, sometimes it will remove the gold or silver coating, means electrode from the samples. So we are providing custom solution for that. So there will be the spring-based contacts. So there will be no scratch will be happening on your samples. And we just have to put sample on the stage and just put cover slide on it, and you can vary the temperature, light intensity, as well the vacuum environment. So based on this type of characterization, you can make suitable atmosphere for your research. So the temperature accuracy is 0.5 Celsius temperature accuracy, and temperature range is -40 to 120 Celsius for the stage 1. And stage 2 having the two micro probes that will can provide the temperature, room temperature to 350 Celsius. Also, we can provide the temperature ranges, room temperature to 600 Celsius. So there will be the depend upon your applications. So this is about the micro probe station. Here is the custom specification is there. You can change the temperature range. You can change the material of the probes. If you require the gold coated or something like that, we can provide this type of probes. Also, vacuum capability, you can discuss with us. We are providing the custom based vacuum. If you want to go for turbomolecular pump, we are also having facility to provide this type of vacuum systems. Also, you can customize the number of probes, 4 to 4 or a number of you can increase. Also, we are providing the temperature control is 0.5 degrees Celsius accuracy, and these all our parameters are controlled with our custom based software. So there will be no any buttons for the control parameters. So it is the totally automated systems. Also, there will be the provision of number of stages, 1 or 2 stages we can provide. Also, with this system is capability to connect with the SMU, light source, and gas feeds. Also, you can connect the LCR meter, CRO, or the solar simulator like this instrument. This instrument also having the capability to connect with that. There will be the control in, we are providing the manual as well control, but we are offering the automated fully software for the control the parameters. So application, we know that there will be the application for the optoelectrical characterization, gas sensing, material science. There will be the applications of this. Here is the one little video regarding the introduction. Video is visible and audio is also there.
Yes, yes.
Okay.
Yes.
SATS, Semiconductor Analysis and Testing Solutions. Are you working on material science, solar cells, thin films, supercapacitors, transistors, photodetectors, memory devices, gas sensing, or diodes? SATS, Microprobe Station, is your ultimate solution for precise measurements and analysis. This advanced low-temperature microprobe station offers a remarkable operating range from -40 degrees Celsius to 120 degrees Celsius without liquid nitrogen. With a robust vacuum capacity of 10 rest to -3 torr, it ensures an optimal environment for your experiments. The station features a lid with a quartz optical window, perfect for optoelectric and photocatalytic observations. Additionally, the chamber functions as a Faraday cage, offering excellent electromagnetic interference shielding, which is crucial for maintaining the integrity of your sensitive measurements. Furthermore, this versatile microprobe station is compatible with a variety of instruments, including LCR meters, potentiostats, CROs, source meters, and solar simulators, making it an indispensable tool for your research and development. Choose SATS Microprobe Station for advanced, reliable, and versatile research capabilities in your lab. Thank you.
Now is our another product is the hydrothermal autoclave. We are manufacturing the autoclave from the base material is SS316, which is pharma grade material. So there is the high quality and non-magnetic material, SS316. Also, we are providing the inner vessels with the PTFE material, or for the higher temperature, we are providing the PPL material. We know that the Teflon is having temperature range of 220 Celsius. You can operate, and PPL you can 260 Celsius. You can operate this autoclave. So we are providing the outer shell is thicker to sustain high pressures. Also, we are making in the variety of the volumes. So you can we are providing the range of 25 ml, 500 ml. With also we are providing till the 2500 ml. of the hydrothermal autoclave. Also, our another product, it is the automatic reaction kettle. There will be the provision for the, you can see the vacuum, means pressure gauges are connected to the system, as well the inbuilt heating and inbuilt steering features are there. So there will be the no requirement of the muffle furnace for the put the temperature. Also, there will be the cooling facility. So there will be the not waste time for the cooling. So heating, cooling, and pressure. These parameter you can control through the automatic reaction kettles. And automatic reaction kettles offers the high pressures. So there will be the high pressure you can make the reactions. So this is the autoclave, hydrothermal autoclave, as well the we are manufacturing the automatic reaction kettles. Small video recording. Please.
Welcome to SATS Semiconductor Analysis and Testing Solutions. Introducing SATS high-quality hydrothermal autoclave, expertly crafted for superior performance and reliability in high-pressure environments. The outer shell is made from premium non-magnetic 316 stainless steel, ensuring durability and resistance to corrosion. Inside, the vessel is lined with research-grade PTFE, Teflon, or PPL, providing a chemically inert environment for sensitive reactions. Our autoclaves feature a thicker outer shell to withstand high pressure, enhancing safety and functionality. With a range of internal volumes from 25 milliliters to 2,500 milliliters, SATS hydrothermal autoclaves are versatile and suitable for various applications. Whether your research involves material science, chemistry, or any high-pressure synthesis, our autoclaves are designed to meet your needs with precision and reliability. Trust in SATS hydrothermal autoclaves for your advanced research and development projects. Thank you.
Thank you for watching. Another product is the sample holder. We know that in the solar cell or something like a, hello? Any query? Okay. This is the sample holder for the solar cells and thin films. We know that the solar cell and thin films having the number of strips, it is called the pixels. So generally we have to change our connections between the ground to the individual pixels and measure the individual IV or CV graphs or impedance graphs. So there will be the having some mechanical connection. We have to generally we are making the connection with the crocodile pin. So it will scratch on the coated material as well. Sometimes it will remove the coating. So we are making the custom solution for that. And this is all manually pixel switchable. So just put your sample on the sample holder, and the regulator we can change the connection of the pixels. So just plug and play. Just plug the SMU, connect your SMU with the sample holder, and put the sample on it. And you can through this regulator you can change the connection of the individual pixels. Also, we are manufacturing temperature-based sample holder as well as the vacuum-tight sample holders for the degradable material also. So this is the sample holder for the thin films and solar cells. It is having the spring contact to reduce the risk of physical damage while ensuring the material and proper grounding, ensuring the electric safety. And also this sample holder can connect with the LCR meter, potentiostat, optoelectrical characterization equipments. This is about the sample holder. Yes, in image you can see that solar cell is mounting on the sample holder. So through this pin you can see that connection is a spring-based contact is made. Here is our one sun light source for the optoelectric characterization as well for the PEC setup. If we are providing the efficient and reliable light source for the solar cell and optoelectric characterization, this is having the functionality is we are offering the wide range of spectra. Also, you can adjust the intensity through the custom software. Also, it is the compact in size, and also it is the user friendly. There will be no requirement of liquid cooling. Also, it is having the in compact in size, and also these provide the color temperature and the wavelength as near as the natural sunlight. So it is the color temperature is 5600K, and it is the white color is the sunlight. For the optoelectronic characterization, solar cell, and the PEC setup, you can mount this light source on the micro probe station chamber. So it is our water chiller, industrial water chiller. It is having the rapid cooling functionality. It is having the 400 watt rapid cooling. Also, it is offer -5 Celsius to 55 Celsius temperature range. Also, in the compact size, there will be having the 5-liter water tank. Also, there will be the inbuilt water circulation pump. It is in there. Also, it is the safety feature, something like the water circulation stop alarm. Also, fault and error detection system. It is there. We know that the application of this, it is having the wide use in the support of the supporting equipment as a thermal laser systems, thermal evaporators, sputtering systems, globe boxes, etc. And it is the industrial grade water chiller. So here is about the PEC setup. PEC setup having the UV or white one sun light source. Also, it is the you can connect through the light source with the direct, or you can connect with the optical fiber. Also, control of the light, it is having the intensity control, and you can chopping the speed control. Also, you can having the light source having the capability of provide the pulses. There will be the calibration for the light. It is a photo sensor. It is there for the intensity control. And the PETC setup is made from the quartz. There will be the quartz window for the light incidence. This is our PEC setup. Regarding PEC setup, we have one video.
Welcome to SETFOS Semiconductor Analysis and Testing Solutions. Introducing SETFOS. At SETFOS, we are thrilled to unveil our hydrogen generation system, designed to revolutionize the way we produce, store, and utilize clean energy. This state-of-the-art system combines cutting-edge technology with robust engineering to offer a seamless hydrogen energy solution. Our proton exchange membrane PEM electrolyzer stands at the forefront, producing high-purity hydrogen greater than 99.9% at an impressive rate of 2,000 milliliters per minute. Operating efficiently at pressures up to 1.5 millipascal, it is perfectly suited for integration with renewable energy sources, ensuring scalable and reliable watt output. This process highlights the efficiency and potential of hydrogen as a clean energy source, making our system an invaluable research as well industrial tool that performs the entire hydrogen cycle from production to power generation. This integrated system not only champions sustainability of hydrogen as a future energy source. Join us in leading the way to a greener, more sustainable future with SAT's advanced hydrogen solutions. Thank you.
This is about our PEC hydrogen generation setup. Also, we are providing the custom quartz glassware, something like the disc or the beakers or some tubes. Also, custom size and in shapes. So these are our valuable customers from the last year. We provided our systems in the Hyderabad University, IIT Gandhinagar, IIT Delhi, Police Academy of Science, Poland, Warsaw, High Hind Vacuum, ISA Calcutta, CUG Gujarat, Shivnadar University, Manipal University, Pandit Dindayal Energy University, NISER, NFSU, and CUG Gujarat. And Purvanchal University. These are our customers of the micro probe station from the last year. Thank you. Thank you for getting in touch with us, and thanks for your time. Also, Ravi sir is requesting some one demo for the micro probe station. So I will give just little one demo about how our micro probe station is having the functionality and capability for the material science research. Just a minute, I will share. You can see the micro probe. Here is the micro probe station. It is having the quartz optical window. Here is the four micro. Can you make full screen? Just a minute. Yes. Here is the 4 micro positioners. It will travel in the X, Y, and Z directions. So I am giving one little demo how to connect your samples. So I have 2 samples. One it is coating samples, conducting coating samples. It is having the photo detector. So it is can.
Zoom it, please.
Hello.
Zoom it, please.
Hello. Audio. Your audio is not audible.
I can hear you, but your PPT is not properly clear, and it just zoom it.
I shared one video.
Yeah, video.
Yeah.
Can you launch it? Because it is very.
Sorry. Hello. Hello.
Actually your screen view is not limited mode. So people full screen cannot be visualized. People want on full screen mode.
Okay. I'm using the mobile phone. Now my screen is visible. Hello. Now my screen is visible.
Yes.
It is visible. Hello.
Yeah,
Yes.
it is visible.
You can. Yeah, I am using my mobile for showing probe station. So I am connecting one. I have 2 samples. One it is the organic photo detector, and another I have the solar cell. It is there. Here it is the solar cell. You can see here. So here we know that here it is the one ground, and here it is the this is called the pixels 1, 2, 3, 4, 5, and 6. These are the individual pixels, and these both side having the ground connections. So I will connect this ground with individual pixels. For here, I am connecting ground to the coating layer. So I am here is the control for that. So you can change the temperature. Here I am showing just a manual control because my laptop is in that meeting connected. So I am just giving little brief. I am here setting minus 15, 16 Celsius. So this probe station having the rapid cooling. So you can see that how temperature is moving. And this stage having the cooling and heating facility. So your sample can you can change the temperature based characterization. Also here, if you connecting your rotary pump with this KF25 connector, so here you can see the value of the you can see the humidity of the chamber. I am mounting sample. Now I am connecting the probes with the sample. So first I am fixing some. My screen is visible. You can see how the probe is connecting to the sample. So both pins are connected. Hello. Hello. Am I audible?
Yes,
Yeah, you
yes.
are
Yes, yes.
Okay. And you can see the video. Okay. Okay. These two pins are connected. And now I am connecting the potential state with the probe station. Potential state is connected. Now I am putting the lead. I am connecting the vacuum pump through this connector. So I can make vacuum. Now it is connected with the vacuum pump. Here I am connecting the optical light. So we are providing the independent wavelength based light also. So we are providing the wavelength based light. So you can see that it is our light source, ultraviolet light source, how it's connected to our, now it is mounted on the chamber. So there will be the no optical noise, it is there. And also if you want to make characterization under the dark mode, just off the light and put this light source on the chamber lid. So it is the blue light source. We having the RGB light source. Here is the red light. So it is directly passed through the quartz window. You can get the characterization data. So it is our light source, RGB light source, and you can change the temperature. So if you want to feed the any gas, just change this port, and the MFC will be connecting through this port also. If you want to with some circulation mode, you can connect rotary pump or diaphragm pump through this port. So here is the two ports for the SMU connections. Here it is two ports for the SMU connections. So there will be individually you can connect the pins with the SMU, and if you have dual channel SMU, you can directly connect two samples at a time. And now I am changed the temperature. It is 260 Celsius. It is showing the temperature of the stage where the sample is put. Now it will sustain and maintain the temperature. So this is about our micro probe station. Any query regarding this micro probe station? Please ask.
So participants have any query, then you can ask to our speaker related to probe station. And for SETFOS training, we will continue at 2 p.m.
I have one query.
Yes.
Sir,
Yes.
about the samples, I want to know about the samples. When you are putting the samples and you cover it, RGB will be blinking. The light will be generated, RGB, sir.
Yes.
Any instead of RG gray or cyan, because you said that we will go for the AI and ML. Okay, got my sir? Got my point?
No.
So I am talking about the when the light is only RGB or grayscale. Can you find the grayscale or cyan scale?
Yes. You just.
Spectral analysis. I'm talking
yes.
about the spectral analysis, sir.
Yes. You just give the some which type and which wavelength you are required. We are providing as per your requirements.
Okay. That means it can also identify and calculate the spectral length range. Am I right, sir?
Yes.
And it will also form the rotatory form, also translation form. Both two can be obtained from this analysis.
Yes.
Okay. Thank you.
So in this micro probe station, you can change the parameter something like the temperature. For the stability and degradation, you have the vacuum capability is there. So you can make vacuum or gas, purge any gas. And also the 4 tungsten tips, it is there. Also the light intensity control as well. You can, yes, one is asking the tip size. Tip size is the 50 micrometer. It is fine micro in size. And also you can change the light intensity as well the wavelength. So you can generate a wide range of different parameters and change the different parameter and get some fruitful outcome. So it is totally made in Indian product. And last few years we are selling across the world. Yes, please. Any query, please ask. Also, there will be some add-ons if you require some vibration-free table. Almost system it is vibration-free. So if additionally you are required some type of the vibration-free table or something you like want to add some cameras and something for the microscope, if you want to require, we are also providing some type of customization over there.
So one customer is asking what is the maximum temperature we can set?
Yes, there will be the two type of stage. One type of stage is you can change the minus 40 Celsius to 200 Celsius. And one another stage you require, it is having the temperature range of room temperature to 600 Celsius. So as per your requirement, if you want to both stage in single system, we can provide.
So customization is also possible. If any participant customize according to the requirement, we can customize and offer to the customers.
This system is very compact, 23 centimeter in diameter, and the height is something like 7 to 8 centimeter. So it is quite compact.
So thank you, Darshan sir, for giving your time and showing presentation to our participants. If any questions, please do let us know. And kindly back to all the participants at 2 p.m. We will continue the session on SETFOS Software. Till then, there is some little bit break. Please be back at 2 p.m. Thank you.
मैडम टेली कम्युनिकेशन पढ़ा रही हैं मैडम उसमें फिर अपडेट्स आ रहा है आपका नाम
हेलो, आवाज नहीं आ रही।
Hello? Yeah.
Hello. Hello.
Hello. Yeah, participant, we will start the next session at 2 p.m. Please wait.
Welcome back to all the participants. Thank you for your patience and your time. Let's continue the session. Kindly wait for 2 minutes. Let it join some other participants. Then we will continue the session on LEDs as well as tandem perovskite solar cells. In the meantime, I can provide you some more information. Like this is our Impulse Technology Innovate Your Research channel. It is our YouTube channel where whatever video, whatever equipment, webinars, demonstrations we organize, we update, we upload everything on our YouTube channels. So the Provi stations which you have seen, the SETFOS earlier demo, nanotechnology, quantum technology, all the information related to solar cells, Laos, QTCAD, nanodecal, rescue, whatever all the product, the domain which we are working on. So we have also prepared past video on different applications. So you can search our YouTube channel in your search box by this name, Impulse Technology Innovate Your Research, where you can find couple of videos are uploaded, which may help you in your search domain. I will start to continue the session within 2 minutes. In the meantime, this is our YouTube channel. And if I talk about the publication list using SETFOS. You can find this paper publications. All paper, solar cells, light scattering, diffusion, perovskites. So this is paper on solar cells. Multi-scale simulation of reverse breakdown in all perovskite tandem photovoltaic module under partial shredding conditions. These are many papers are available on our website as well as Google Scholar. You can find a lot of publications. These are all papers. And some of the blog is also available. You can also see the blogging, aging characterization of high band gap perovskite. In the blog, every information, if you will read it, you can find the information, how you can boost the efficiency or what parameter it will affect your device analysis. So that kind of blogs is also available, and that information you can get from here. So these are all our hardwares for characterization of solar cells and simulations. Sorry. Now let me start to demonstrate the software. So we'll go to the continue the session. In the left side, you can find this left area. This is all example regions where many examples are present inside the directory of SETFOS. Whatever kind of device you want to simulate, mostly all device example are given in our library, which you can scroll and you can find it. You can also try to simulate and see the variation of different analysis. So these are different analysis based on different applications or different search. Now I would like to start one LED device, then we'll go for the tandem perovskite and all overall feature of the tool. So this SETFOS can perform DC, AC, transient and impedance analysis. Now I want to take one device for the LED. So I want to click on file option and click on new options. And in this new, I want to do the same thing. I have to add the number of layers. I click the middle layer and click on add button to add the number of layers. So here I will define my substrate name as example glass. This is my ITO electrodes. Then I want to take HTL as a whole transport layer, emission layer, and then next I can take as an electron transport layer, and next layer I can take as an example back electrode, and then air after that. Now I want to define my thickness of this all layer. Let's suppose glass is having 100 nanometer. This is ITO 25 nanometer. This is HTL, which I can take 30 nanometer. Emission layer, I can take 20 nanometer. And this is ETL, which I can take 90 nanometer. This is aluminum back electrode, 150 nanometer. And this is 100. Now I have to mention this ITO as electrode. To define the electrode, we have to enable the dipped diffusion modules. And I have to set this ITO as electrode. Similarly, I will click on aluminum and set this backside aluminum as electrode. And in between HTL, emission layer, ETL, these I will set as a semiconducting. I will define its property also. But this middle layer, emission layer, I will use as a transparent layer. Also, I will set this emission layer as an emitter. For the emitter, I need to enable this emission module. I will click on this toggle emission module and I can click on this emitter so that this bulb sign will enable and emitter setting will be enabled. So this kind of layer structure I want to create. Right side layer stack thickness and this energy level we will modify you because I have not assigned the material property till now. Only the front end layer structure visualized I have set. This is my emission, this is my HTL, this is my ETL, this is ITO and aluminum. Now emission module is enabled, dipped diffusion module is enabled. Absorption module will not be required for LED case. Now we have to define the refractive index of the layers. So I click on this glass layer where the refractive index of glass is constant. So I can define the constant value of real part, that is 1.5. And then I can click on this ITO layer and I have to define the refractive index. So as in told in the first session, that you have to assign the refractive index optical data. So if it is not constant, you have to upload the value. So file tabulated data, you can import it. So I am going to import from my library. If the material was not present in library, then I have to create from scratch by defining the wavelength, real part, imaginary part, as I told in the first sessions. So I find out in my library the refractive index of ito.nk file. I select it and click on open. You can visualize this preview of the refractive index with respect to wavelength. Value can be visualized by click on edit and this is NK data with wavelength dependent. Similarly, for all layer along with the ITO, I have to assign the refractive index optical data. I mean, by option the file tabulated NK and click on import HTL work functions. So ITO I selected. For HTL, I have to choose which material I want to use for the HTL layers. And let's suppose I want to take NPV. NPV as a whole transport layer. So I want to import here and want to assign the refractive index data. Then I click on this emission layer and choose the file tabulated.nk format. Upload the library material data. So let's suppose I want to use balq.nk. So optical data is present in .nk extensions. EM represent for electrical semiconducting material and PL stand for photoluminance data. I need to upload first of all optical data. So I selected and uploaded. Then I click on this ETL layer, file tabulated NK value. And for ETL, let's suppose I want to take, I take ALQ. So I selected ALQ.nk and select open. It is now assigned. Then click on aluminum, select on file tabulated NK data, click on import and select al.nk file and click on load. Now all material reflective index data I have uploaded. I have to mention the electrode work function as well. So this is my ITO electrode and I will go to the electrode settings. I have to choose injection model, ohmic type or thermionic type. So I will select here thermionic model. And define the work function. Let's suppose work function is equal to 5.15 electron volt. And similarly for aluminum, where I can choose thermionic and the work function I can take 3.25 electron volt. And in between the electrode, these are all semiconducting layers. So I have to fill the semiconducting tab. Go to this semiconducting tab because I enable this checkbox and semiconducting tab is enabled. I want to hide the layer structure tab for time being so that I can visualize my backend. Now here, either I can, as in the morning session, I explain how to add the charge transport property. So I can mention the charge transport property here. I can define this box. I can edit the value of HUMO value, LUMO value, density of state, dielectric constants. And I can enable the doping type, acceptor type, P type, and define the concentration, whatever concentration I want to do, optical generation efficiency and mobility models. This time I want to import from my library because the procedure is same for all the tabs. Either you are putting your own value or you are importing. Multiple options where you can upload your material files or you can fill these information in different checkbox. Either it is related to HUMO, LUMO, dielectric, density of state, doping, mobility, and tabs. You can add the tab. This is exciton tabs where multiple excitons can be enabled. In the exciton tabs, you can mention the radiative decay rates, non-radiative decay rates, generation efficiency, diffusion constant, saturations, annihilation rates, triplet generation, triplet singlet generation, and TADF from low energy to high energy transfer rate. The TADF or energy transfer rate can also be mentioned with the exciton polar and quenching for electron, exciton polar and quenching for trapped electron holes. Charge transfer models is also there. This is completely exciton tabs where you can enable and mention the parameter of excitons in this checkbox. Similarly for traps, you have to add the traps and mention the traps parameter and mobile ions and recombinations. I am importing the HTL emission ETL semiconducting layer material file from the library. So I click on this, selected the HTL layer, click on import. Now this time I want to take HTL constant .em file. This is semiconducting file and click on open. Now these parameters, electron mobility has been filled, hole mobility has been filled from that file which I imported. Doping is not mentioned, dielectric constant is mentioned, Lumo is mentioned. And these parameters are not mentioned, so it is not there. Similarly, for emission layer, I click on the emission layer, click on import. In the emission layer, I want to use the emission layers. So let's suppose I want to, multiple emission layers are there, depending on your requirement, because parameters are varying, changing on different emission layers. So I selected this emission layer and I uploaded. So that's why this parameter which you can see here automatically filled. These parameters are auto filled from the EML3 file which I uploaded, including this energy level, dielectric constant and HOMO-LUMO. This is field dependent mobility are used. Then I select this ETL layer, electron transport, click on import, and I will choose here the ETL layer by pressing E and find out ETL.em file and upload. So one thing is that this EM file is also simple or notepad file. In notepad file, you can mention all the property like charge transport property, traps, recombinations, excitons in the notepad and save it .em. And similarly, it is mentioned already in our database. So I'm uploading from my database. So I choose here and it is uploaded. These are uploaded, including this excitons, traps, recombinations. If you want to check the script, you can click on this script. From where this ETL data is taken, the value taken in the material file, what is the source? So source is mentioned here. Value is taken by this particular reference paper, which they may be got experimental or from some theoretical things. So which is uploaded here. Similarly for EML emission layer, click on script. If it is mentioned, then it will show here. So I mentioned all the active layer semiconducting property and optical property. In the emission layer, the emitter is also set. This is emitter layer. This middle one where bulb option is showing. In the emitter layer, I have to upload the luminance, PL data, photoluminance. So I can click on this browse button, which contains the wavelength and intensity. So I click on this value. I click on upload the PL data. Where I can take BALQ as a photoluminance data. So these are all photoluminance given in our library. For ALQ, alpha NPD, green, IRPPY, super yellow, NEF data, organic materials. So I am taking this BALQ.pl and uploading. Now this is uploaded. Here you can see the intensity and wavelength. And I can mention it is a excitation 1. Now, once it is done, in the emission setting, this is emission setting where I can define the emission mode. Either I can take spectral mode of emission, dissipation power analysis, mode analysis for outcouple. So there are three emission mode: spectral, which define a spectral emission simulation; variable, which can be swept, are wavelength and energy. This mode is used, for example, to compute the spectral emission or the radiance of OLED. The radiance of OLED, this spectral is used. Dissipation power analysis and mode analysis. There are three options. For radiance, this is spectral, and this dissipation power analysis, which a dissipation power analysis performed, the variable that can be swept are in plane U, in plane K, in plane efficiency. This mode is used to compute the emitted power of dipole versus the in plane wave vector, the second one. And third option, mode analysis, which can be swept, are wavelength and energy, and it can use to compute the contribution to the different optical modes in OLED, outcoupled, waveguide, absorbed. For that purpose, the different emission module are there. It can compute the lifetime of the dipoles. The third one for dipole, this one for radiance, and second one for emitted power of dipole with in-plane wave vectors. And this is called the spectral wavelength. You can use the spectral wavelength. Let's suppose you want to use from 390 and change it from 390 to 700. Here I can select the exciton coupled one. Now it is selected. Emitter has been set. Emitter, we can take single emitter, multiple emitter. That is also possible. Now I can go to the sweep angle. This is sweep mode. In the sweep mode, earlier I sweep the voltage, thickness, but this time I want to sweep angle. So whatever the position I want to take, I can take the sweeping parameter. So let me check emission angle where it is. Let me sweep this emission angle from 0 degree to 90 degree with the interval of step size of 5 degree. And let me give the name of this project as an example, training OLED. And click on run button. So invalid parameter missing, exciton definition in .em, or invalid excitons for emitter layer. So in the emitter layer, there may be some missing parameters. So let me check.
Hello.
Yes.
Yeah,
Yes.
I was not able to hear you.
Hello.
What-
Can you
Sorry.
hear me?
Now you are audible. Okay, thank you. Sorry.
There may be some missing parameter. I have to check it. Okay. So, but not. One minute. Let me open the existing example. Something I have forgot to mention it. So this is one of the similar example where I have taken the same parameter, but maybe something missing. So let me run it, the calculations. Now the simulation is done. Some parameter maybe forget to mention it somewhere. So you can see the ITU, HTL, emission layer. ETL layer, HTL layer, and this is the result window. In the result window, if you click on this device current, you want to see the internal quantum efficiency. Let me show you the display key figures. So this is device efficiency, integrated luminance, radiance as polarized, pre-polarized, current efficiency. We want to see the electrical profile with 0-degree angle. If angle dependent is there, it will display electrical field, and you require to see the optical integrated data. So this is luminance for XY plot. This is a Smith chart. And if you want to see the radiance, this is for radiance. So you can see the XY plot and polar plot from here. And if you want to see the peak emission wave intensity and other spectral analysis, this is emission spectrum at 0-degree angle, at 20-degree angle, 35, 40-degree angle. So if the angle is variation, so you can see how if you are changing on different emission angle, you can plot the normalized emissions also and see the emission spectrums. P polarized, S polarized, and other, including the white emission spectrums. So many opportunities are there in the tool to visualize different emission analysis, including the angle dependence. You can see how the angle dependence, absorptance, reflectance, if angle is changing. So not only single parameter you can check, multiple parameter you can sweep and plot different characteristics. This is for generated photons, current efficiency, luminance, peak emission intensity. Now I have taken till now only one electrical layer, one ETL, one HTL, and then perovskite or emission layer. But multiple combination, if you see here, this is for LED, one of the another example. By following same procedure, adding the layer, defining the HTL layer. In this particular example, there are two emission layers, two emitter layers. This is EML1, EML2. So you can see from here, by enabling this checkbox, emitter is enabled. And this is emitter setting, where one CPB, this is red PL, red photoluminance and CPB photoluminance data. And this is ETL layer. If you see the script is also having different materials. And if you see this emission, the spectral is used. You can use for outcoupled, incoupled analysis, dependent type of emission mode. And this is diffusion settings. In the diffusion setting, you can see the steady states calculation is possible, transient simulation is possible, AC impedance analysis is possible, IMPS, IMBS, intensity modulated photocurrent and photovoltage. So these different kind of drift diffusion analysis is also possible. So let me run. If you want to see the full OLED with doped, including the doping, where the doping it is done, I can show you. Let's see in the, is it done in HTL layer or ETL layer? I'm not find it. 1 minute. So let me see. This is running the simulation, and you can see the reflected color, emitted color, intrinsic colors. In the display key figures, you can find the different analysis. Electrical analysis on the top side. These are all electrical analysis. And bottom side, you can find the optical analysis. This is and optoelectrical at a time. Electrical, optical, optoelectricals. These are all key figures jointly. So dependent on your need, you can take the different parameter. You can plot the CIE color diagram. This is blue, green, and red. So you can plot the CIE diagrams from here. This is optical profile, radiative dipole density in EML layer, because this layer, radiative dipole density is there, EML1, EML2, dipoles. Radiative rate profiles, refractive index, and for emission of two EML layers. In this, there is no parameter sweeping. We are not sweeping any parameter. That's why the right side no sweeping function is showing. If you want to see another example where there is one EML layer but more complex structures. This is high fluorescence JV characteristics OLED applications. And this particular B4 PYMP, this is doped, this is undoped. Some layer are doped, some layer are undoped, and the back contact is also changed. And this is EML emitter layer where the PL data is also you are using differently. Now this time the voltage is sweeping from 2 volt to 7 volt. So let it run. I will show you multiple options of solar cell as well. So this training will give you a full insight about different features, application of the SETFOS. Now simulation is done. You can click on this device current. This is IV curve from 2 volt to 6.5 volt applied, and accordingly it is plotting. If you want to export this data, whatever the output are coming, you want to plot, you want to export your raw data, you can simply right click, click save this data, save image as a PNG file, JPG file, PDF file, SVG file. These are all image format. So you can save either your graph in image format, or you can save this visual data. Save this visual data in the form of text. So this text option is also there. Let's suppose IV, LED, this is can be shaped in text. If you want to save the data in Excel, save IV, LED, Excel. So XLS, you can mention XLS, .xls, it will save your data in this format, Excel format and text format. You can see it is available. This is text format of IV data. Any for solar cells also you can plot, LEDs also. So multiple tabs is showing the multiple out. And this is data which is in Excel. So your data can be exported in single click like that. Now many analyses are there in the tool. You can see different variations, different analysis. Exciton transfer rates are there, internal quantum efficiency, power density analysis, including all electrical profiles, emission profiles, CI color diagrams, luminous efficacy, emitted colors, optical integrated current efficiency, luminance, peak emissions, and radiance. And this is a spectrum, emission spectrum at 0 volt or 2 volt, and 2 to 5 volt, 6 volt, how we are changing and how the emission spectrum are showing. You can see the emission spectrum on the top. And if we talk about the interface, now this is one of the another example where high index layer HATCN with interface, hooping interface in between the two layers, HTL and high index layers, and electron blocking layer, emission layer, hole blocking layers. So EML, EBL, HBL. We can create this electron blocking. So this is master equations model. In the master equation, you can see the singlet and triplet informations. Singlet binding energy, generation, radiative decay rate, non-radiative decay rate, singlet polar quenching rate. Similarly for triplets also. And inter-system crossing, singlet to triplet, triplet to singlet, dielectric constant, standard deviations. This is for master equations by enabling these features. It applicable in LED devices. So this is for electron blocking layer. Similarly for EML, there are two master equations are used. You can check this script for the parameters. This is hole blocking layer. Single master equations are used. And this is ETL layer, aluminum. This is trap features are enabled. So let me run it. This is master equation model, intermolecular spacing, Foster radius, Dexter radius, texture temp efficiency. So let me run the simulation, this full master OLED calculation. Exciton, quenching, depth diffusion, master equations, emissions. These are simulating. And it is showing the reflected color, emitted color, intrinsic colors. These are visualized color. And this is a key figures. Display key figure where electrical key figures are there. And go down, optical key figures and optoelectrical key figures. So these are key value of optical, electrical and optoelectrical. So whatever tau or wavelength, intensity, efficiency, luminance, EQ, device efficiency, these all information in the value form you can get here. In the graphical, you can see here. Similarly, the charge density plot and background information, background physics, you can get to know from the manual and tutorials. This manual background models, equations, master equation model or other equations of related to LED or solar cell in the manual page, and tutorial will help you how to create from scratch of any devices. Like this is exciton density master equations. Excitons read coupled. You can zoom particular regions and it is displaying like this, including recombination, mobility, CI color diagrams, and luminance. And these all are different LEDs example. And for TADF, now this is all about this different TADF OLED. So in the TADF, you can see the excitons energy transfer rates are mentioned here. This is energy transfer rate from to value. And this is from low energy to high energy, thermally activated delay fluorescence with delta E and rate transfers. So let it run this. And this is temperature dependent, temperature variation emission spectrum. Wavelength respective with temperature variation. How do I know? You can see the sweeping value is equal to temperature from 160 Kelvin to 340 Kelvin with 20 steps. So that's why this is the temperature variation 160 to 340 Kelvin. And this is emission spectrum. You can visualize. If you want to see the device current, it is the device current here. And if you want to see the device efficiency, this is the device efficiency, EQE, Lambert-Eaton, and generated photons. Even color filter there. This is to OLED with white color filters. So multiple color filter is often also there. Reflected, emitted, intrinsic color. All key figures value as well. So these are all analysis for the LED. You can also perform based on the number of emitter layers, NPD. So multiple information you can gather. Now I want to show you few example of solar cells as well. So this is one of the another example where glass 1 millimeter substrate, FTO, TiO2, perovskite, spiro gold, full perovskite. So let me simulate sweeping voltage with different value of voltage biasing. So not only linearly you can apply multiple parameter at a time, whatever you are giving as input. If you don't know the value, you can sweep and optimize. We can zoom particular regions and see the graph with doping, p-doping, n-doping, and all those. And this is for power conversion efficiency for full perovskite IB devices. And if you see here, around 13%, 17% efficiency for this particular structures. You can see this energy level. So click on this and see the VOC, GSC, fill factor, maximum power density, conversion efficiency. And this is energy band diagram. So you can zoom particular region, find the LUMO. This is LUMO that we mentioned. This is HUMO, and this is the gap from negative to positive. So till now, I explain about these things. The spectrum which will be used. One thing is that there is inert spectrum file is given in the library. AM 1.5, AM 0, direct, and other spectrums. If you want to upload your own spectrum, then what you can do, you can upload the wavelength intensity in one notepad format like I mentioned in the first session. First column wavelength, second column intensity, and then you can browse that file. So that spectral shifting is possible. You can, whatever the spectrum, whatever the range, intensity, wavelength you want to put, software algorithm will consider it. So that user-defined functionality is enabled in the tool. Not only a standard spectrum. Let's suppose you want to use location. So this is, you can set your latitude, but wherever you are present, there may be some latitude, longitude, elevation, Even date is also mentioned. There is a calendar is given. So what the company are trying, they are trying to develop the realistic spectrum on your device. Realistic spectrum on your device so that you can visualize. You can follow your spectrum. Even cloud weather condition, maybe the weather may affect your device. So that's it. The information about what model is implemented, it is given in manual. Because one day session is not good enough where I can explain everything. But the overview, for the overview purpose, definitely you have may got some knowledge about the product with different features. Till now, I only show you the steady states, but there is a provision for transient, AC impedance, and IMPS and IMPS. Different biasing voltage sweeping. So I want to take another example for, let's suppose, impedance analysis. This is another example for only electrical calculations, not any optical or emissive. The gold electrode, one organic molecule, and calcium electrode. Everything is there. Crypto diffusion setting where AC impedance feature is enabled and the value of amplitude and frequency as an input is mentioned. Amplitude, frequency, input value is given. This is sweep setting where minus 10 volt to plus 10 volt with an interval of 0.5 increment from minus to 10 to plus 10. It will apply the biasing. Now I run the simulation. You can find the electrical impedance analysis. This is your electrical impedance, AC current with respect to voltage, AC analysis, AC current amplitude, AC current phase, capacitance, capacitance component, capacitance normalized, conductance value, normalized conductance, impedance. This is real part and imaginary part of impedance. Red one is real part and this blue one is imaginary part. So this is impedance Z and Z naught. For Nyquist plot, you can export this data, save this data, visible data, and for Nyquist, you can save it. You maybe plot the data between Z and Z naught, real part and imaginary part. So second column and third column of impedance, you can also plot. So that Nyquist plot will be there and including impedance, amplitude phase, mode Schottky analysis, susceptance analysis, many more electrical impedance characteristics are there. These are all graphical representations. If you want to see the profiles, you can click on that, see the real part, charge density in real and charge density in imaginary. You can see it. This representation window is changing for real part and imaginary part. So AC charge density with amplitude. This is with amplitude. This is with phase. This is AC current. So DC, AC, transients, impedance, everything available on single tool, so that you have no need to switch multiple platform again and again. So these are all graphical analysis. which you can plot the graphical or electrical field, potentials, many more things are there. And this is for IV, including the impedance. You can zoom and visualize. This is one of the impedance with illuminating light with ZNO, P3HT, PCBM, P dot, absorption setting, diffusion, and illuminating scaling linearly. Light illuminating. This is light illuminating frequency. You can plot the capacitance in graphical and like that. Similarly, the impedance with intensity scaling. And this is one of the another example where HTL, P3, ALO, aluminum diffusion AC impedance, voltage and aluminum homo value is sweeping from 5.3 to 6.3. 5.3 to 6.3 homo value is sweeping. So any parameter you can sweep, whatever parameter is unknown for you, you can sweep it to find the optimal value. So from it is plotting the multiple graph at 5.3 homo value, 5.4, 5.6. So that's why this graph multiple which you can visualize. It is a different value of homo lumo on different electron volt, the susceptance. Graphical is also there. Now, I want to take another example, then we'll go for the tandem perovskite device simulations. So this is one on another structure where ITU, this is one whole transport layer, interface, perovskite, interface, C60 and silver. This is one of the structure with different thickness, and this is layer structure and energy levels. Now in the interface, you can see enable trap interface. And that trap parameter defines. So in between whole transport, perovskite, there is an interface layer. We are enabling the interface as SRH recombination for this interface, and that trap density, energy, electron capture, hole capture from left to right, interface recombinations. Similarly, for this perovskite and C60 interface, and their electron hole trapping is mentioned. Absorption AM 1.5, steady states. And this time you can see 5 parameters are sweeping. Voltage, C60 interface, trap density for N type, C60 interface top trap density for P type, and for bottom interface trap density for N type and P type. And the range of voltage from 0 to 1.1 with a 0.02 volt sweeping, and the concentration of trap density is also sweeping. So you can optimize your value, multiple or single, dependent on your particular need. So I run the calculation, it is finished. You can click on this device current. Now this is device current multiple graphs. This red one is representing the current density without recombinations. This blue one is representing with recombinations. This green one is representing Langevin recombinations. And this is for SRH recombinations. So multiple graphs are plotting based on that particular recombination things. Without recombination, with recombination, Langevin, SRH recombinations. So 4 graph according to that 4 particular parameters. You can see the graphical representations also by seeing near about the recombination things. You can click on this trap interface trap current. And since trap concentration we are changing, we are defining the trap concentration here 1.1 e to the power 12 to 4.1 e to the power 13 or 14. That's why the variation of the trap concentration, how the interface traps are affecting. So all are there. Similarly, interface trap density. This is power conversion efficiency. Multiple graphs. You can take any one. You can also select it. It can plot. If you want to see only at one value, it is plotting at 1 e to the power 8. You can change it. It can plot single value also or multiple value. If you will enable this checkbox, show all, it will plot all power convergence efficiency plot. So 1 by 1 or all can be plot at a time. Similarly, the power density analysis. And this is electrical IV key figures. Where concentration dependent, maximum power factor, open circuit, maximum power conversion efficiency, band diagrams. This is the band diagram from 0 volt to 1.1 volt. And all parameter can also be exported. And this is for photocurrent.
Then yeah.
And this is all analysis which you can plot. Now, the hopping interface is also there. So interface which will not be available in other tool, including the PLAD and all those things. Now I want to show you some example for energy yield calculations. Solar energy, so glass, ITO, P dot, P3HT, PCBM, aluminum. And this is the location time, latitude, longitude, angle. Click on run button. This is energy yield, cumulated incident spectra based on direct spectrum, cumulated diffuse spectrum, direct spectrum, and all curves with date and time. In daytime may be different spectrum, night time may be different spectrums. So we can choose the different intensity, solar angle, because if you see here, the date which is mentioned, you can take today's date, and in the sweep setting, you can change this date. You can take next 4 days, 5 days, and let it run. Solar energy yield with time dependent. So you can take 28th September, 29th, 30th September, solar angle, incident intensity, energy yield value is equal to this. So this is energy yield key figures, and this is for photocurrent on different day and time zone. So this pink graph is representing the P3HT PCBM ISC. This graph is representing the aluminum. This green one is P dot, and red one is called the ITO, glass, sorry. And this ITO is like overwriting to other materials, which can be visualized. If you will hide one layer, this red layer, you can hide it. It can be visualized. So this is overlapping glass and ITO. We want to see this AQE, quantum efficiency. So this is one active layer, E dot P3HT PCBM. And for EQE analysis, this is AC EQE with wavelength dependent, wavelength respective, and voltage from negative to positive. Quantum efficiency, AC. And this is multiple voltage respective graph of quantum efficiency, AC amplitude. Similarly, if you want to see the responsivity, photodetectors, it is also possible. This is for responsivity graph. If you want to see the external quantum efficiency, this is external quantum efficiency from negative to positive biasing. And this is photocurrent. And this is one photocurrent external quantum efficiency of solar cell in one cell. So multiple cells also we can plot the graph. This is solar IMPS. Absorption module is enabled. This is responsivity and many other characteristics are there. AC charge density. So it is a very broad tool. We can say it's a very broad tool. And let it come on the final device that is called the Tandem Perovskite simulations. This is one of the Tandem Perovskite silicon conform structures, where you can see so many layers are there, including the interface. 3D ray tracing is also there. To enable scattering for this layer. Coated interface is there. So all coherent layer around the interface are treated as a conformal coating. You can see this one in coherent layer, and coated interface. So coated interface is an interface between an incoherent layer and a stack of coherent layer. And coherent layer are treated as a conformal coating on the textured surface of the incoherent layer stack. For this particular, you can see the scattering type, 3D ray tracing. Other option is also there, Fourier, Gaussian, statistical microtexture, Phong, Lombardian, these all models are there. Even predefined geometry, microlens, pyramidal array, cylindrical array, linear grating. These options is also there. So whatever type of the nanoparticles or related interface you want to include, you can enable that. And this is a RMS setting. You can define the root mean square setting, diffusion length, and all those things. So use the random surface generator to create an interface with a given roughness, so exponential and Gaussian. And this is import file. You can import the textured data, like PV textured data. This is PV textured data, you can import it. PV lab texture data, you can import invert texture. That kind of option is also there. So multiple scattering, 3D ray tracing, let it simulate this tandem, perovskite, silicon conform, and rear structure. Both can be possible. Now it is done, simulation is completed. You can see the goniometric interface properties scattering on different angle, diffuse, texturing, and 3D ray tracing option is also there. This is for incident conform structure, and texture can also be visualized in 3D ray tracings. This is like second image. You can see the multiple textured rays are there.
Yes, sir. Please. Yeah.
You can see another angular scattering air interface on the bottom and top for different materials. And this is optical profiles. This is scattering reflectance at 800 nanometer wavelength. Down conversion is also air silicon to interface. Now I want to take a rear texture that was confirmed, and this is a rear texture where different other materials are taken. These are different materials with their refractive index property are assigned. And for that, advanced scattering modules would be required. So you should also confirm your package, whatever maybe in future you plan, the module available in that. So tandem perovskite silicon rear texture. And let it click on this 3D. This is 3D image, incident ray, and click on this arrow. This is green one is called scattered ray, blue one is called incident ray. We can click on that and we can visualize our analysis. Angular scattering. This is for textured tandem perovskite silicon rear textured. Now let me go to the multiple layer tandem solar cell devices. This is one of the another structures where MgF2, top ITO, SNO2, C60, perovskite, nickel oxide interface, multiple terminals, multiple junctions. Mid ITO, amorphous silicon, silicon buffer, N-type, P-type, intrinsic, HTL. So many layers are there in this particular structure. So all optical electrical property is defined already. In absorption, AM 1.5 spectrum from 300 to 1200 wavelength. Steady states calculations with voltage applying from 0 volt to 1.2 volt. 0 volt, 2 volt with a step of 0, 1.0, 1.5, 1.55, 1.6, 1.65 random value, not linearly. And let it run this complex structure also. It may take little bit more time as compared to previous one because the number of layers are around 10, 15, 10, in between 10 to 15 in this particular structure. So little bit time will increase. Now it is done. We can click on device current. This is device current, IV curve with recombination, with bimolecular recombination, and this is without any recombinations. We want to see the display key figure around 28% power conversion efficiency in this particular structures. VOC, fill factor, maximum power density. These are all electrical key figures. at this voltage 1.7, around 28% power conversion efficiency can be achieved. This is power density. And if you want to see the electrical profiles, you can zoom particular this region where maximum layers are present. We can zoom it. This is the junction. So we can, let's suppose, remove the LUMO. This is LUMO. And this is reference voltage biasing variations. And we can extract this data. So all analysis, whatever you want to plot, you can see here and you can zoom that regions. I hold the right button and draw the rectangle. That will visualize all the analysis characteristics. So similarly, whatever you want to visualize, you can see here and you can plot it. This is stack contribution for different layer, which is showing in the right side. And if you want to apply some resistance with your device, you can see in the steady states, in the drifted diffusion, not only a steady states, it can perform the transients. So the transient mode is enabled, selected, then transient signal. You can apply the electrical signal. You can see this is the transient preview. Their constant value. This is the label 0, duration 2 seconds, label 1, duration 1.8 seconds, and this is 1 second. So this is a preview of this signal, transient signal preview, electrical transients, and temperature is also possible. So this is a transient preview and transient solver with their iteration points. We want to define some electrical circuits. You can mention the device area and series resistance, parallel capacitance, lateral resistance. You can attach the circuit with your device. And you can plot the transient also. This is with respect to time from 0 to 2 second or 3 second time steps. Circuit voltage, balance transient, device transients, device current, power voltage. Even there are some other options is also there in texturing, Lambatian, Pong, BHDF, Fourier, statistical microtexture, or nanoparticle effects. So now I think I have tried to explain many of the feature of the tool. If you there is some time for the question and answers, so participants can ask your queries so that I can show you that particular feature which you may be interested in your particular needs. I hope many things are clear from today's training, because still everything is cannot be possible. I have shared you the feedback form in the chat box, so you can mention your feedback about this training. If any questions are there, you can type in the chat box, or you can unmute your mic and ask me directly.
Hello, sir.
Yes, please.
Sir, I am audible.
Yeah, you are audible.
Right, sir, what is the steps for measuring photo detection devices?
What is the
Photo detector devices. Measurement process.
photo detector simulations, right?
Right.
So responsitivity you can calculate for photo detector by using this tool. 1 minute. Let me take one example. Like this is one of the example OPD. In that SRH, IV, OPD, organic photo detectors. So this one is simulated. You can see the IV, and even responsibility analysis is possible. So photo detector only, not fully for photo detector, but it is somewhat possible. Some paper is also published on photo detector by using this tool. So we are sharing the feedback link. Just a minute. So feedback link is given in the chat box. Participants can fill their form. If any questions are there, you can let us know. This software is commercial. If someone need trial version, if you are interested in purchasing of the tool, because it is a commercial tool, so this need to be licensed version, purchase one. So if somebody interested in trial for few days, then you can let me know. We can try to arrange a demo version, and after the demo version, you should also plan to purchasing if any possibility.
Hello.
Yeah,
Sir.
please.
Good afternoon, sir. What is the cost of the license, sir?
So the cost of the license is basically dependent on the module. As I told in the presentation, there are two things are dependent. One thing is that module. Second thing is the validity. So which module is required? How many modules are required from out of these four? Let me show you. One thing is that the validity, 1 year, 3 year, 5 year, 10 years. So we have multiple options: 1 year validity, 3 year validity, 5 year validity, 10 year validity.
For
Number
4
of
modules for 1 year, what is the cost, sir?
For 1 year, let's suppose this 2 module as an example, absorption and diffusion. This 2 module will cost around 3 lakh plus GST, around 3.5 or 3.7.
Okay.
Under 4 lakhs for 1 year validity.
Okay. Thank you, sir.
Yeah, thank you. So you can contact to my email ID if someone need the license for demo or purpose or to test it. You can just drop an email. This email ID, you can drop it.
Sir, for demo purpose, how many days we will give the permission?
It will be only 1 week.
1 week.
Because the demo license is just to show the capability, but in the training you already understood many of the capability. So the main objective of the company is just to sell their product. But demo license and demo training is just to show you how this tool is, the feature exists, is it beneficial for the customer or not. But from the papers, you can go some papers available in good journal. From there you can get to know the capability of the tool. And demo version just for 1 week, I think, or maybe 1 month we can also try. With limited restriction will be there. There will be a
Okay.
couple of restrictions that.
Okay. Okay. Thank you, sir.
Yeah, thank you. So if anyone have any requirement or any possibility to arrange funding from your institute, then please do let us know or ask the quotation from us and we can offer you. Thank you from our side. Thank you for your time, and please submit your feedback on the link which we have given in chat box, and we will keep in touch with you. So thank you to all the one. I am closing the sessions. Thank you all.